Hello, my fellow YouTubers. This is Roy back again, and Vinny. Vinny's just chilling. Alrighty, so we're building this thing, and we're going to add some electrostatics in the center. And I got these copper. I'm going to refine this, but this is just kind of a markup. And you got little copper strips on the outside. We're using Lexan plastic as a dielectric. As well, I brought in some glass. I got some more glass to bring in, some bismuth. So far, the way we have this set up is it's a compass heading the wrong way. So let's do that to it. There we go. So that's your north. That's your north. Inside here is your south. And the top is the south. And watch the compass when I throw it in there. there's some electromagnetic field in there. It's pretty interesting. It'll stick to that because the only thing on metal on here would be the compass itself. So I guess I'll write out a circuit for this whole thing. We're going to add some capacitance. We're going to add some more paramagnetic and some more dielectric. And we're going to continue this unforeseen, I would say, project. Leave your comments, but if you're curious, why am I bringing in the electrostatics? Because frequency and high voltage does come into play here. And pretty interesting stuff. I want to add a couple more coils. I guess on the other side, I'll add some coils. We get the top one shaking. Now remember, these are both south, so they're opposing each other in the middle there. So there's some compression there. And if anybody knows any difference between generators and dynamos, leave your comment. And what I'm referencing to between the two, a good friend of mine, Bill, explained to me that you have 9 magnets, you take 2, you flip them over and get them close together to where the last 2 become like a separate dipole of the string of magnets, and it's compressible, and it gets you more current. You see the top is reacting. Now, like I said, this is just a markup. I guess the more I meditate on this project here, the more things will become clear. But Walter Russell had brought some good enlightenment. And with the Walter Russell, he talks about the vortex. But on top of Walter Russell, I got to bring in what is his name? Jesus, I got the paperwork somewhere. But the double helix. And the double helix would be similar to the double cone, to where the ends, the high pressure would be the smaller orbit, the lower pressure would be the wider orbit, and in here, the lower pressure here would be the wider orbit, and the higher pressure would be the smaller orbit. And with that being said, you're going to have electromagnetic field around the outside of this whole array. And I can see it to where, you know, I have north facing out, and everything in the center is south. So everything's being drawn into the center. And the reaction of that environment, that apparatus in this environment, would be how it performs, and how it performs the back part of that performance would be the ether's reaction. So the ether is the ether is the Lenz's law effect. And the action has a reaction as equal. You can't get any extras out of the in or the out. And this is proven. This is empirical data. And why I come up with projects like this is because the only way you're going to really kind of find something is you have to go outside the box. But you have to use the empirical data as the empirical knowledge as data for what the laws are, whether it's a Lenz's law or Maxwell's equations, or it's my boy Tesla. So you have here your electrostatics. So what we'll do is we'll get the center closer, and then you got your plastic, which are metals, your dye, your paramagnetic materials, your conductors will be on the outside of that plastic. So from the MIT video, if you guys haven't seen it, it's called Dissecting a Capacitor. It's a great video because it shows you that the electric is stored in the dielectric. I gotta give a shout out to my boy Terry Woodruff. Haven't yet got a chance to talk to Terry. We've been bouncing on this YouTube stuff for every bit of 6-7 years together. And I want to give a shout out to my boy Tesla Rod. My boy Ryan. Never talked to Ryan either. I guess in the beginning I left a couple comments that I probably shouldn't have. And I think I hurt his feelings. And apologize, Ryan, but past that, I'm sure you are. And yeah, I haven't had a chance to talk to him, but I really appreciate Ryan's Tesla experiments, because it brings the electrostatics in. And I think he's a lot like me, to where there really is no plan, there's no end game. It's about the journey through the experiments. And hopefully you guys enjoy that journey with me because, yeah, I mean, I don't know. I'm not in it for the money. I'm not in it for fame. I'm in it to share, to learn, and to experience this thing we call electricity. Because there's a lot more to it that we don't know. What we do know is how it acts, how it reacts, how things are associated with it, and how it becomes opposing to a magnetic field. So basically, what I'm saying is, if you look at the L shape, that your linear would be your, I believe, your dielectrics, and your horizontal. No, your horizontal be your dielectrics. I guess it doesn't matter if it's horizontal or linear, but you got your dielectrics and you have your magnetism. And when it comes to electricity, they're 90 degrees off from each other. And there's your L right there. And your 90 degrees would be an L shape. So enough babbling. Hopefully you guys enjoy the start of this project. I had great questions. I'll keep answering them. Bring them on. If you have any suggestions, bring them on. We're looking at a smaller ring for high pressure, outer ring for low pressure, just like sort of like a tornado and a hurricane. Not saying I'm creating that, but it's similar because you have what we are creating here is a magnetic field in motion, okay? And what the centrifugal force of that motion is in relations to the one speed and the circumference of that diameter. And the smaller you get with your diameter, the tighter it gets. And the reason I even brought in dielectrics, or should I say electrostatics, there's so much here because there's a lot going on in the middle of this. I mean, I pretty much could tell you electromagnetics is all over the place. And what I will tell you is, the strange thing is when you bring a load up to this wheel without a core, you would think that it would put strain on the wheel, but the wheel seems to get faster. So I'll have to hook up the right meters here for load in, load out, for the driver, for the turning of the wheels, the driver coil. Also, bringing in 4 driver coils and splitting it up to where they're all using, 2 separate different pickups. But I want to separate the bifilers. There's a lot going on here with this experiment because I'm learning a lot more on the bifilar coils. There's no electromagnetic field in the center. It seems to be having a unique kind of feature to where it's taking the air that's inside there and it's rarefying it in a sense to where the electromagnetic is only on the outskirts here and loops back in. And when it loops back in, it's going to the backside of these magnets that are here. But everything, the metal that's on the spokes and the rim and the core is iron. So that is bringing in the dipole from not from here and the back of the magnet, from here into the center. So the dipole is being expanded out. So what I'm thinking is that the ether is going to have to react to that. So how is the ether going to react to this? And that's the questions. And this is part of working through this experiment, where if the ether is going to be the backdrop to everything you do to it, whether you bang a hammer on the ground and then you're dealing with material that you bang, or you're in airspace like this and you're creating two separate components that are a difference in potential. And the reason I'm bringing up potential differences here, because the low pressure and the high pressure would mean that the high pressure would be the difference in potential of the low pressure. So there's going to be a unique situation in the center which the ether is going to be responding to. That's why I put some conductors in the middle, which right now are spinning the opposite way. We could spin them the same way, and trust me, all the experiments will be top, bottom, whichever way they're spinning, versus Mother Nature's medium. And what I mean by that, versus how a compass right now says to me that North Pole is that way, South Pole's there behind me, and East and West. So your dielectrics would be your East and West, and this compass shows me, and your magnetic would be your North and South. So how this thing is not oriented to anything, but it's sitting in place. So when you were to take I gotta watch my hand here. If you were to take a compass and stick it into the environment, magnetically it doesn't really, it doesn't follow the Earth's. All right, so you can see right now where north is, correct? And then you can see out here where north is. So with the medium, we're changing the medium here. That's what I'm getting at, is where if the medium is the Band-Aid or the rubber band, that's a better way, the rubber band. And you take that rubber band and you pull it back or you push it away, you're gonna have some kind of tension you're creating. And this is it. This is the machine that's going to get us through a lot of good experiments. And I have a lot more of these glass inserts here, shelving. They're tempered glass, so they're hardened glass. And what I was saying earlier in regards to the dielectric, how the MIT video, which you guys got to watch, where it shows if you separate the capacitor, the Linden jar, the Linden capacitor, is where you would have the charge go in the top as a positive. You would have your negative in the bottom there. You put your dielectric in the middle, and guess what? Once it's charged and you separate it, you can touch every part of all three of these and nothing happens. All the charge is in the dielectric and right here. And this plastic, it can be plastic, it can be glass. Glass is a lot better dielectric than plastic. But it goes to show you that the charge is really in the dielectrics. So we're going to bring the dielectrics here, because now we have the electrostatic high voltage. You need the high voltage. You definitely need the high voltage. And right now, that won't bring in the lens effect by bringing this high voltage into play. So I can throw them in the capacitors. Now the capacitors will have collectors coming off of these, go into the separate capacitors, just like a Wimshurst machine. and you'll have two separate charges, two different potentials. So that means that the difference in potential here into the capacitors, meaning that the smaller wheel is turning faster. So that means there'll be more electrons going into one plate of the capacitor. The upper capacitor, or the other capacitor to the upper wheel, which will be the low pressure, will have slower turns, less turns, which less pressure going in the capacitor, and you'll have a difference in potential. So this is what I kind of mean, or this is what I really mean, on the difference of potential with the high pressure, low pressure, meaning that one turns faster than the other, which creates, if you have a capacitance, it creates a pressure in the capacitor. That means that one part of the capacitor is going to be being pushed electrons into it, and then in the capacitor from one plate to the other, there'll be a slow down dielectric, and that dielectric will be those plastic plates there, as well as glass. I don't know where I'm going with this whole thing, but I can tell you right now, the more we turn the wheel, the higher the pressure in the capacitance, where it'll become too much for the volume, surface area, or volume space of that capacitance, meaning like there's this outside aluminum here would be one surface area, and the inside is another surface area, and basically this can only hold so much before that, and then this spacing between here and here will just bam and release it all, balance itself out. So we're going to create that. So what we're going to do is have the capacitor set up to where they release, and when they release, they don't have to release to loss. They should release to something that's going to hold that charge, sort of like lightning in a bottle. And lightning in a bottle means, to me, is that we could take all that energy and store it in glass, or any dielectric that we want to create, which would also be like my capacitors here. Now, these capacitors are good for certain things, but not for storing energy. These are good for handling current and a lot of energy. So when these are in play, they're good for passing it and juggling the ball. Not good for storing. I want to get into storage, because I think if anybody would even waste their time on something like this, would have some kind of idea that down the road you'd be able to have a simple machine like this, to where it stores energy, or electrostatics converts it to a storage cell, which would hold maybe 1 or 2 amps in current, but maybe a lot of voltage. And that would allow the surplus to be there all the time for you. Because I'll tell you what, we're ruined. Mankind's ruined. You know why they're ruined? Because of our consumption. If you look at our lights, if you look at our washer, dryer, our sprinkler pump, our pool pump, our air conditioning, our heat, our usage in electric, whatever we plug into, it's a lot. We keep going further and deeper and deeper and deeper into dependence of this thing that we use as electrons, like slaves. Electric is a slave to man. It's not supposed to be that way. You can't use it all. Even though it's more abundant than we can use, you can't use it all. There is no regenerating electricity. There's taking it from places. So that's how I look at it. So this would be something that creates an effect. This effect would be a cause and effect. So the cause that I'm creating creates the effect. The effect in response is collected, and that collection will go into capacitance. And it could be in different capacitance too. One thing I don't know if you guys are familiar with, but these things are called supercapacitors. And supercapacitors are just using different parts of the element in the periodic table that won't suddenly release the difference in potential. It just drags it out. And that's what we're going to get into as well, because the release is just gone. The energy's gone. It's Big Bang gone. It's gone. The medium absorbed it. But we want to store it. Lightning in a bottle, I call it. We want to store it, and we don't want it to come out like lightning. We want it to go in like lightning. And that would be the Big Bang, kind of the capacitor. Boom! Difference in potential, high and low, and it releases, but it's caught. But the question I'm going to put out to you is, what has the best memory in your metallics? Put that out there. What metal has the best memory? You don't see that metal here anyway. Well, you do, but you don't. And there's more of an alloy, mixed metals to make those magnets. And you just see power go on and off. That's not good. That's the real deal, McField, is meaning that the power company just did that, not me. What if the power goes out? Why do I want my lights out right away? Who wants them out right away? Guys, Broham. Peace out. Leave your comments. 27 minutes, 28 seconds, and over.